Okay. Okay.
Okay. Our next speaker for today is Lev Radzivilovsky. He will be talking about something three-dimensional.
Right.
Please.
Thanks. So, I think we, as Israel students of Boris, are very lucky that he decided at some moment to come to Israel. And I learned a lot from Boris, both in mathematics and around. Like, I think for me, important thing was how to grade Olympiad papers, and the secret of trade was that you should be liberal. And well, and I want also to use the opportunity to thank the organizers twice, because they almost did it in 6 years ago, 2020, and then Corona came and it had to be cancelled just a couple of weeks before. So something exciting happened to me just before the previous date, when this Kanevskyfest was supposed to happen. I have learned a new skill, which was creating three-dimensional creating animations in there is this program which is called GeoGebra, and it is very user-friendly and easy to use. So takes a few moments a few minutes to see the basic features if somebody shows you. And I was really happy about this new skill, and I wanted to use it. And so when Aran came and told me about this idea to make this special day in honor of Boris, I thought that I want to present to make some animations. And actually, I have prepared two stories. I believe that about the first story, people will tell me that they know it already, because there are many students of Boris, and he probably have told them. But I want to present it with animations. And the second story is more recent. So there, this is the problem. Everything I tell you in the first part is what I learned from Boris. And we have this pyramid, tetrahedron, and we want to find its biggest planar section. The planar section is biggest area, and this problem has an interesting history. It was created during entrance exams to MGU, Moscow State University.
Oral exams.
Oral exam. Yes, you probably know this better than me. I'm not from Moscow. Oral exams is where the magic happens. Yes.
Yeah, exactly. If you call it magic, yeah. Which up down.
So for those who are for younger people here who are not from Moscow, Moscow State University is the best, the most prestigious university in Moscow.
Was.
Yes. No, it isn't.
Okay.
You're right. Not anymore. And everybody wanted, not everybody, but people who are interested in mathematics wanted to be accepted. And then there should be entrance exam, because Moscow State University can't accept too many students. And during the entrance exam, there is the written, which is more or less objective because everybody gets same questions. But in the oral exams, you come to the examiner, and the examiner gives you a question, and you are supposed to solve it on the spot. Maybe you are given this several minutes to think.
20 minutes in general.
20 minutes, okay. There was a much easier problem in some Moscow Olympiad, which was known before that. What is the largest section which is a triangle? And this is easy. But then
What is known about the pyramid?
the answer is no. But
No, so what is given?
tetrahedron, any tetrahedron. No, not regular.
No constraints, just arbitrary.
Yes. And the answer is, if examiner understands that there are reasons not to accept you, he will give you a special question which is more challenging, right? And this is one of such questions because, and after you fail your test, you come and you ask different people, maybe you know some teachers or mathematicians, and even if you're given much more time than 20 minutes, this question is still very hard. So, I saw Boris told me about this question, and also I saw him telling some younger people about these questions, and most people don't solve these questions. Actually, Boris told me about 2 people who solved this question. Maybe there are more. There is Bershon solution and there is linear Strauss solution. Bershon is David Bershon. It's not the next speaker, but closely related to him. And linear Strauss is Elon linear Strauss. Well, so for triangular section, it's really easy because you just move one of the vertices, and I mean, at one of the endpoints it is the greatest because area of triangles base times altitude, and you want this point to be as distant from the. So here you see it better. You see 2 projections, it's proportional to the length of this interval. So it's clear that it's greatest at the endpoints, and then you do it to each vertex one by one, and you conclude that it is probably the
Face.
face. But then there are quadrilaterals, because whenever you cut the polytope with a plane, the faces of the polytope are the sides of this plane. And since the tetrahedron has 4 faces, it has at most 4. And the answer is actually the same. The best is still the face, but it's much harder to prove. So I start with Bershon approach. We make all points 100 times more close to this section. All the vertices of the tetrahedron become 100 times or maybe million times more close to the section plane, and then we have when we do it, the section is still the same, but the faces are smaller, and so there is no reason not to do it.
But still theoretically, you have 6 edges of the.
Right, but just you say that it's most hexagon, right? But you have only 4 faces. and each face, like face is half space. The tetrahedron is the intersection
So
of.
is it obvious that the maximal area is not achieved on a quadri?
It's no, it's very hard.
uh,
That's why it's a good question for the oral exam. and even outside oral exam, it's not easy. After we do this projection, we have a big quadrilateral and there is inscribed small quadrilateral, and we want to show that this inscribed quadrilateral is no more than one of the four triangles. Triangles when you just drop one of the vertices. But it's not precisely correct, and here's a counterexample. Here we have some square, we have inscribed quadrilateral, and it is greater than ABC and then ABD and whatever. So during the projection, we forgot something important, and this important thing is 3D Menelaus theorem. If you have a spatial quadrilateral, just 4 points which are not in the same plane, and you intersect it with a plane. A plane intersects every edge. And there are, you compute the ratio of.
You mean every face?
No, every edge. I'm not. Okay, you can think of it as a tetrahedron, but I think of it as spatial quadrilateral. You have 4 points, and you connect them in cyclic order. And then the even
The blue edges do not exist.
yes, the blue faces should be erased, and actually I do erase them in the next slide. So you want to show that Menelaus three-dimensional version of Menelaus theorem claims that the product of these ratios is one, or in other words, that if I this part of intervals I paint them in green and purple and green and purple and so on, then the product of green intervals is the same as the product of purple intervals. And and here is the proof. We project everything onto a line which is orthogonal to the section plane. And sort of Thales theorem, for instance, AP divided by PB is the same as A prime L divided by LB prime. And after the projection, everything cancels out, right?
Yes, now I see.
So when we project when we turn our problem into dimensional, we should not forget that we are not interested in arbitrary inscribed quadrilateral, but quadrilateral which is which respects this Menelaus three-dimensional theorem. So if the ratios here are like alpha and 1 minus alpha, and it doesn't mean that this interval is 1, it means that the ratio is like delta to 1 minus delta, then alpha, beta, gamma, and delta should satisfy this formula. And then we can actually prove that the area of PQRT is less than the maximum of these 4 triangles, ABC, ABD, and so on.
So the quadrilateral that I see, the large one, is the intersection with all the faces?
Yes, the large quadrilateral is sort of what happened from the tetrahedron. But for instance, ABC is what happened from the face ABC. Remember, I took all points very close to the section plane, right? and now it's we turned a three-dimensional problem into a two-dimensional problem, which is much easier.
How it's relevant that all the vertices are close to the plane? Yes, how is it relevant?
Because your tetrahedron is essentially quadrilateral. Oh, it is a very. It is still in space, but this is very.
I only zoom on this.
It's almost yes. You just zoom down the z coordinates,
Squeeze it, yeah.
squeeze it right, and then this planar problem is still challenging, but much easier. We have this. I denote as A and as B and as C and C the areas, and the greatest among them is called S max. The least among them is called S min. And for instance, if you look at the let's say this triangle, it can be expressed as C times gamma times 1 minus beta. Because you have the same corner, but you make shorter sides, so the area is smaller. And we need to show that the maximal triangle is greater than SPQRT, but it is the same as to claim that the minimal triangle is smaller than the four triangles around the.
Today in the morning, we'll listen to a talk of Misha Bell, which exactly discussed this kind of question. So, how large or small can be the area of a polygon inscribed into a smooth curve?
But smooth curve, not in a polygon.
Well, this is there are two key differences. This is not smooth. It has angles, and the second difference is that we have this Menelaus condition.
And the third difference, that the Misha's problems were not offered for oral examination. For whatever.
No, the art is that the problem should look very similar to something which you can really solve in 10 minutes. And so now we have to prove inequality under some constraint. The inequality is what here you may safely assume that S A and B and C and S D are all equal to S min. Then the inequality becomes only harder, but actually it becomes easier because S min cancels out and you have just this. So now it is pure algebra. You have to prove this inequality under some assumptions, and now it's not even geometry, it is algebra.
Your problem becomes affine for quadrilateral. So you can deform quadrilateral to any shape you like.
Yes,
And
but
it will be
not all quadrilaterals are the same. So
yeah.
So then
This Menelaus condition may fail here.
Is it affine or not?
No.
no. Again, what's the question?
Whether Menelaus condition is affine. If you do affine conformation.
Yes, sure, but still, okay.
But the laterals are not all affine.
Yes, not every quadrilateral is square, but anyway, we did cancel out the s's, so now we are in this algebra problem, and the algebra part is nice, but it's not exciting. Maybe I'll skip it. And as usual, you come to the fact that the arithmetic mean is greater than geometric mean, and that's the first solution. And the second solution, which is due to Elon Linistrauss, who was supposed to be one of the speakers in the 2020, is even more magical. So you rotate this section around its diagonal. And here you see it at different angles. here P and R are projected in a way that it is the same point. So the quadrilateral is separated by this PR diagonal into two triangles, and the base is always the same. So it's important to maximize the sum of altitudes. But you just see those altitudes in the lower picture. And so it seems now it's again a planar problem. You have a quadrilateral, this quadrilateral, and you have this line, the orange line, which goes through the intersection of the diagonals, and you want it to be as long as possible. And the claim is, which is pretty intuitive.
Why P and R coincide?
I projected it in the, like whenever you want a line to become a point, you just look in the direction of that line.
There is only one direction.
So I just projected so that it will become a point. And then the length of projection is precisely the length of the altitude of the triangle. And then it is pretty intuitive that among all the possible orange intervals, the diagonal is the longest, and the diagonal corresponds to a triangular section, and then we are done because it is easy. But okay, so this is the two-dimensional problem. Now, why the diagonal is the greatest? I probably there is some other explanation, but as I understand it, it is the convex function of the angle. Like there are two parts. There is this orange interval and this purple interval, and each is a convex function of the angle. And why is that? Since it is a continuous function, it's enough to prove that this m is less or equal than the angle bisector is less or equal than the average of the two sides. And why is it obvious?
Because you have parallelogram.
Because actually the bisector is located between the altitude and the median. So it is less than the median. And even the median is less than the average of the two sides. And that's the first story I wanted to tell you. And before I go to the second story, I will tell you something about colors. You know, if you want to get a good picture or good animation, you want to have a nice, bright, dominant colors. And you might have noticed I didn't use the red color in the animation at all. And I will, and why? Because this day is supposed to honor Boris, and Boris doesn't like red color. And I will tell how do I know. Just 15 years ago, I have invited Boris to give a talk to Olympiad students, and there was a whiteboard. And just half a minute before the talk started, I gave him some whiteboard markers. So for some reason in my right hand, I had some colder colors, like maybe blue and green and black. And in the left hand, I had some warmer colors, like I think I had red and orange. And well, I come to Boris, I suggesting these are the markers and these are reds. And he took the colder cards, but said, but he declined the reds. And it took me a few seconds to understand why. But then so he went on with the talk, and the picture turned more and more complicated. And at some moment he required an extra color. So he said that maybe he will accept the red, But by then I understood why red is undesirable, and I said, but I have orange, and he told me that orange is much better. So I didn't use the red at all in this presentation, but I did use a lot of orange, of course, blue, and
Because the orange is pomarańczowy.
Okay, so the second story is from Israel Mathematical Olympiad. There are several nice stories that I could have told, but I have chosen this one. It's a nice geometric story, but also because it's there is Boris have taught for many years, and the age difference between his older students and his younger students are probably decades, and therefore I wanted to present something which is related to some younger student of Boris, and this story is related to Omri Solan. And here it comes. It starts with a problem which was invented by Yoav Krause and Omri Solan. We say that parabola embraces a circle, or in original Hebrew, parabola michabeket ma'agal, if they have two tangent points. And here is the original Hebrew. And then you have three circles, three parabolas, and each parabola embraces two different circles. And the students were asked to prove that these three parabolas have a common tangent. And actually, when I saw this problem, I really liked both the problem and the solution.
Exile all three vertices to infinity.
No. So here is the proof. In Hebrew, we call them Yerhuv. In Russian, it's called Vychod Пространства. Maybe I shall use the word specification. I'm not sure it's a real word, but just for this talk. We construct a plane which is parallel to the plane of the picture. And then we construct three spheres. Each sphere intersects this picture by one of the circles, and all of them are tangent to the same parallel plane, to this, let's call it a ceiling. Like this is the floor, and there is also a ceiling. So all spheres are tangent to the ceiling. And then for each couple of spheres, you may construct a cone, so that all the lines of the cone will be tangent to both spheres.
That's what I suggest.
Was it? Maybe you're right. So, I heard something different, but you're probably right. So anyway, then all the cones have the common tangent plane, which is the ceiling, right? But they have yet another tangent plane. Like you can consider the plane which goes through all the centers of the spheres, and then you can reflect this plane in reflect the ceiling with respect to this plane, and you get the second plane which is tangent to all the spheres. Now, this second plane, actually, the cone, how does it intersect the picture? It is intersects the picture in the parabola, right? Just because when you intersect the cone, you can get either ellipse, parabola, or hyperbola. But if the plane is parallel to some tangent plane of the cone, you get the parabola. And actually, you can see from the theorem that those parabolas are unique. So this second tangent plane intersects the picture in this orange line. And
I remember it was Pascal's construction of solution of some problem. This spirit.
maybe. Actually, I think this problem was inspired by the older problem, which I have learned from Boris. Should I come back to this? Or this is there is the question about.
Well, but you still didn't say why there is one line tangent to the parabola, so you did.
I did because consider the second tangent plane to all the cones,
Yeah.
which is symmetric to with respect to the center plane, and it is tangent to all the cones, both in space and in the picture.
Ты делал симметрию через центры сфер.
Да,
Плоскость через центр
плоскость через центр сферы, относительно нее я отражаю потолок.
Я решил, что ты через первоначальную плоскость делал.
It's tangent to the cone, but also the ceiling is tangent to the cone.
Yes, but ceiling doesn't intersect the picture. We have chosen to be parallel to our picture.
No. How the ceiling is parallel here?
Okay, the construction is the following. I take the plane which is parallel to the picture. I call it a ceiling.
But it's not tangent to the spheres.
After I construct the ceiling, I construct spheres. Like maybe I will draw it. Like this is picture. This is ceiling.
The spheres are not centered in the center of the circus.
This is circle.
Centers are not living in the original plane.
Yeah.
This is circle, and this is the sphere. The sphere doesn't have to be centered in the original plane. It depends on the size of the circle.
Yes.
And then
Then you reflect not with respect to the floor, with respect to the centers of the.
there is a plane of the centers, right? Like this. There is the ceiling, and there is the other plane, which is the tangent to all the spheres. And in the plane, there is tangent to all the parabolas. Because in the picture, in the original picture, the cones are parabolas, right?
Yeah.
So I think it was inspired by this problem, which I learned from Boris, and I believe they learned from me. I'm not sure. That you have 3 circles. For each pair of circles, you take a couple of tangents. And these intersection points are on line. This is also solved with 3 spheres, but different 3 spheres. These spheres are symmetric. They have the same center as the circles and the same radius. And then you have this plane, which is.
So this is exactly the problem by Pascal.
Is it by Pascal? I thought it was called Monge theorem, but I'm not sure it's his solution.
No, the idea of replacing 3 circles, 3 spheres, and looking at the 3D tangent planes, appeared in some of the brilliant books of
It was invented by Pascal.
elementary mathematics,
I didn't know who invented it.
mathematical circles, so something like this.
Well, it's very famous. I'm not sure who was the first to invent it. But then when Yav told me about this problem, he told me about a slightly more general version. You can replace this parabolas by maybe ellipses or hyperbolas, and you can say the following: if the 3 conics have one common tangent, and there are the circles which they embrace, then you get yet another common tangent. Just parabolas are 3 conics which are tangent to the infinite line, right? And then I thought about it for some time, and I understood that this is a T-short question. So what is the t-shirt question? Maybe not everybody is familiar with the term. So this is a t-shirt. And in Israel Mathematical Olympiad, we try at least once a year to invent some nice geometric problem, which has some picture. Just when and we print it on. First we give it in the exam, and then after the exam, the students receive T-shirts.
Do they accept Magen David?
Yes, it should have. This picture should have a Magen David or something a bit Magen Davidish, right? And that's and what it does to a problem that when people talk to each other, they wear this problem, right? So when they talk to each other, they look at each other, they are reminded of this, and then it causes them to think further about this thing, and then that's one of the reasons why this thing was generalized more than once, because people continued to think about it. So how can you generalize? I do have more time, right? Yes, I do have more time. So we shall take inspiration from Pascal theorem, which generalizes Pappus theorem. Pappus theorem is the following: you have two lines, you have 3 points on each, and then you construct 3 crosses, and the intersection of the 3 crosses are on one line. And Pascal theorem is more general. It's for an ellipse. It took more than 1,000 years to come from Pappus theorem to Pascal theorem, but as it happened, we can try to repeat it without waiting 1,000 years, right? So well, Pascal, I'm not sure if he proved it at first for circle or for radius, but it is a projective theorem, so it's true for any conic, and it's also true for hyperbola. And you can take a hyperbola and degenerate it in a couple of lines, right? And here is a generalization. And what do you see here? There is a big black ellipse around everything. There are smaller blue ellipses, which are hugged by the big black ellipse. And there are circles, which are each circle is embraced by 2 conics, by 2 blue ellipses. And I want to say 2 things about this picture. First, that this is rigid. For instance, if you erase one of the elements, like you know there are 3 blue ellipses and the black, and you know there is the orange and the green, but you don't know about the purple. I can prove that the purple exists. Or if you know the 3 circles and you know 2 blue ellipses and the black ellipse, I can prove that there is another blue ellipse. So that's what I mean by rigidity. And the second part is that the focuses or the focuses of all the ellipses are on the same ellipse, which is confocal to the black ellipse. This is the gray ellipse. The gray and the black have the same focuses.
The picture then is not realistic. Both sides of the blue ellipses cannot be so close to their boundary.
Well, why not? They are. Why?
No, the picture is correct. No, actually, the focuses are much closer to the vertices than most people think.
Depends on the shape.
Like if you draw something like this, and some people say that this the focuses is not true. It's more like this.
Really?
Yeah.
Well, there is probably some optical illusion because it looks that they are not on the diameter.
Exactly.
What
Yeah,
I missed
they-
here?
With diameter, there is no diameter.
No, for each of the blue ellipses, I can draw the large diameter, and
But you may be confused between the vertex and the tangent point. It's not the same.
yes, this is optical illusion.
It is yes, there's an optical illusion. Because they are thin.
So where is the vertex? Say that.
Well,
Takes the line.
The vertex is here, and the tangent point is here.
This is vertex.
Yes. So, in a way, it does generalize the famous Salmon's billiard theorem. What is what does billiard theorem say? That if you play billiard on an elliptic billiard table, and one interval of the billiard trajectory touches the ellipse, then each interval of this the black ellipse and the blue ellipses are confocal. They have the same foci. But this is just another way to look at it. Maybe I should explain why it's the same. You have a couple of confocal ellipses. One is like this. Another is like the larger one is the billiard table. So by optical property, you know that this angle equals this angle. By Salmon's theorem, you know that this angle equals this angle, right? Therefore, the red angles are also equal. So the billiard ball running along this line will be returned along this line, right? So here you have a couple of on this picture you have two black lines and two gray lines. So I want you to think about a couple of black lines like a conic. So if one of the focuses of this blue ellipse is on this line, another should be on this line by Salmon's theorem. And I want you to think about a pair of black lines and a pair of gray lines as a couple of confocal conics.
No, there was a classical theorem which probably was known to Greeks that if you have an elliptic billiard and shoots forward a trajectory, then it would be in general tangent to some smaller ellipse.
Precisely, that's what I'm saying.
Or something like this.
But I've read somewhere that it is to that this theorem is of George Salmon from 19th century, but I might be wrong. I'm not sure.
I'm sure it's according to.
Maybe someone in the ancient Greece. Judas?
Called consular ellipses.
Well, yes. Actually, I heard people call it Poncilia theorem, but I have read somewhere this is Salmon. I'm not sure. Maybe.
Integrability of the planar billiards in focuses.
Yes, it's related to planar, and actually there is a case when the billiard is between the foci, then the lines are tangent to confocal hyperbola, and so on.
Right, there are cases when the internal ellipse generate, transforms into a hyperbola with the same possibility.
Yes. Okay, it's a nice theorem. I probably won't prove it right now, but I will say about this book. There is a book by Arseny Akopyan. The first edition was at first in Russian, then it was translated to the languages. This is the second edition. It's much fatter than the first edition, and it contains more examples Actually, before he made the second edition, he wrote an email and asked whether we have some new things to show. And this picture was among the pictures I sent him, and this was his favorite, at least between the pictures I have sent him. So
You should have sent it to the International Agency of Atomic Energy.
The picture on the left, which appears here as animation, it is in the first book, but it is this is a generalization which is not in the first edition, but it is in the second edition, and more or less it's equivalent to the picture I have shown you previously. So wait, what happens here? So
Okay, practical question.
yes.
So to prove the results of this story, can you say look for a projective transformation? that
Well,
makes everything
it's
to
tricky.
circles?
It's tricky because the projective transformation don't circle into non-circle sometimes.
No,
But
it does preserve centers, that's true, but circles to circles it does.
no. Okay, I think I might have time to prove it is specification. There are actually two specifications. One, when we turn the two-dimensional picture to three-dimensional picture, and in the second, we turn a two-dimensional picture to four-dimensional picture. So maybe I shall try to explain it very briefly, because there are further generalizations. So what happens is the following: we turn the orange circles into spheres with the same center, the same radius, but in space. Then we turn
Ellipses.
the ellipses into rotational ellipsoids. And then there is one more ellipsoid. It is a gray ellipsoid, which is tangent to the smaller ellipsoids along ellipses. And that's the idea. Maybe I should leave it like this and not explain it in
Where
detail.
is the gray one?
Well, now it exists. It is. I'm not sure.
It's different from the original one? Like,
Yes, you try to, for instance, there is this black ellipse, right? It is in the horizontal plane. You can sort of enhance it to a symmetric ellipsoid. And whenever this ellipsoid touches this sphere, it turns out that it touches this ellipsoid by an ellipse, and it means that it also touches this sphere, and so on, and that's the idea. I think I want to say remark also on the more exciting four-dimensional specification. What you see here, this is a cylinder, right? And inside the cylinder there is a rolling orange sphere.
Just orange.
Yeah, okay, for brevity, rolling orange, right? And this orange intersects the picture along the circle, and the circle is embraced by the ellipsoid, which comes from the cylinder, right? Which is really fun. At some moment, you see that they stop touching each other, but it is because you see incorrectly. Because you look on the real part of the picture, and if you look at the imaginary part of the picture, you still see the tangency, right? And the two, I could roll it even further, but then you stop seeing the intersection. So I stopped it at the points which are the moment that the orange is tangent to the plane. And when the orange is tangent to the plane, you have this circle of radius 0, and it is still tangent to the ellipse, but in imaginary point. In 2 imaginary points. It is embraced by an ellipse. And that's the idea of 4-dimensional split. I should stop.
There's no tangent to the ellipse.
I
It's
don't think about.
tangent to the plane containing the ellipse.
It is okay. I claim that if this is the focus of the ellipse, I claim that circle of radius 0, it is still tangent to the ellipse, but in non-trivial points, in the complex points.
This is a famous picture that illustrates the focal property of the conic section.
Yes, the tangent spheres, precisely. Do I have 5 more minutes?
Yes.
What about that? Yeah.
Okay, so how does the 4-dimensional specification work? You take this largest orange circle, you turn it into as a sphere, right? And this is the radius of all spheres. But then this is 2-dimensional plane, this is x-axis, this is y-axis. But you add 2 more coordinates, there is u coordinate and v coordinate. And then you take some vector which is, it has x direction, but it also has u direction. So when you go to the right, you get farther and farther from this plane. And the y vector, you add some slope in v direction. So you have those 2 vectors span 2-dimensional plane in 4-dimensional plane. And whenever you consider a point on this 2-dimensional plane and a sphere around it of precisely this radius, you get those circles. And that's the idea. And then, all the union of all possible orange circles is precisely the interior of the black ellipse. But what are the foci? If you remember the previous picture, focus is when it's the dangling sphere. Focus is when the orange touches the plane of the picture. So here, the foci is you should take let's call this radius of the orange up. The foci are precisely the points on the tilted 2-dimensional plane, which are a distance r from this plane. So you intersect this tilted plane with the r cylinder around this plane, and the cylinder intersects the plane at an ellipse, right? And then this ellipse is projected into this picture, and this is to show that this is confocal. But if I have half a minute, I would rather tell you about how to generalize it even further. So here's the inspiration. There is a famous Poncelet theorem that if there is a pair of conics and one conix is inscribed in the other, you want to draw a polygon which is inscribed in one ellipse and search to present another. Then you can rotate this picture. Even if you start from here or from here, the line will close after the same number of iterations. And here I have vertical, horizontal, vertical, horizontal. This is called Cayley theorem. And then you can do projective transformation, and instead of vertical horizontal, you can have 2 points, and some like wood lines will be through this point, and different lines will be through this point. And then I claim that Cayley theorem is a special limiting case of Poncelet theorem. Poncelet theorem is more generic. So why is that? And here is the picture that explains this thing. If you have a very thin ellipse and you have some polygon which circumscribes it in the broad sense of word. That you look at the lines, not on the intervals, then when the ellipse gets very thin, you get this picture, right? So precisely in this sense, just the family of polygons which circumscribe some ellipse, when ellipse gets thinner is so in this case you say that Cayley is special case of Poncelet, but if you know Cayley, you might guess that it generalizes to Poncelet. And that was what was done. Do you have a minute? No.
The Poncelet theorem is valid for the rotation numbers bigger than one. So you may consider a polygonal trajectory that makes two turns,
Right.
3 terms, and what is quoted as Cayley theorem corresponds to the rotation number 0.
Aha. Yes, but my point is how to get the generalization. Easy generalization would be to take what we know already and to do projective transformation. So instead of so actually a circle is a conic which contains these 2 points, right? They're infinite imaginary points, but it's maybe a fancy way to define a circle, but it's correct. But then you do projective transformation and send this couple of points to your favorite couple of points, and you get an easy generalization. But harder generalization is just the same as to jump from Cayley to Poncelet. You replace conics containing 2 points by conics which embrace the same conic. If this conic turns out to be a very thin ellipse, it is the same. And so this was an attempt to generalize it. You have 7 conics, and some of them embrace others. But in which way? This is the graph of the vertices are the conics, the edges are the embracings. And then if you have the graph which is a form of a cube without a vertex, you can add the 8th vertex of the cube. Now this is not precisely correct, but it's 1/27 correct. And I probably don't have time to explain it in this sense. So it's some algebraic geometry which yes. So thanks. I think I should finish.
It's a naive question. Would you explain the proofs of all your results to the ancient Greeks?
Again? Sure. Whenever. Whoever wants to listen.
I mean, that's
mathematics. So everything was known to.
To ancient Greek. Boy, I didn't hear the last part of the question. But
Can you speak in Greek?
I should have to tell him some elementary things about algebraic geometry, and then.
But nothing which really was behind what they knew about. So what is the name of this genius who wrote books on conic sections? Apollonius, yes. So Apollonius could well.
I'm sure he would love to learn algebraic geometry.
I agree.
No, they he had a sandbox.
But without no without teaching him some news 19th century thing, probably not. It depends how long he will listen.
Okay. Accepted.
But it's mostly on Rislan and on Repair and other people. It's mostly not mine. Yes.
No, so I mean the distinction between the elementary mathematics and some more deep results from algebraic geometry, which probably.
They are somehow connected to each other. But that's precisely the part I didn't have time for.
For example, knowledge of complex numbers is helps, but is not really necessary.
No, okay. There is this 19th century trick called Jewish coefficient. It should, it has to be explained, and it has a nice analytic geometry, but
Okay.
Are you planning to use these
You
problems
can have-
on entrance exams?
You can ask the rest of the questions later on, okay? Let's,
okay. The answer is no.
well, let's think of it.